Hi there. Let's talk about how polynomials work. We'll take them into the lab. We want to look at the connection between an equation and a graph. So first of all, take a look at this graph. Where do you see its roots? Well, they're right here, and there's one right here. So it looks like the numbers -5 and also +2 are roots. Now, let's make a number line where we put those numbers down, -5 and 2. And let's shade where the value of the function or the output is positive. Well, you can see only after 2 are we positive. Up until that point, everything is negative. So here's the positive region. After we do a few of these, we'll look at what the point is. Now, let's look at the degree. There's a couple of different ways to find this. One way is by looking at the equation. You have a first degree factor and a second degree factor. Well, just add those together. 1 plus 2, the degree is 3. Here's another way to do it. Trace along the graph, and every time you turn around, count that as a separate number. Here's what I mean. Watch me as I do this. 1, 2, 3. There's your 3. Now, some textbooks will say, look at the turning points. Here's a turning point, here's a turning point. If you add 1 to the number of turning points, you'll get the possible degree. We also call it the least degree, because sometimes degrees can be hiding. It can be very deceptive. So we know the equation, so we know for sure this is third degree. My description of the graph would be up, down, up. Let's take a look at another one. Its roots are at -2, +2, +3. So -2, 2, and 3. Let's put those on a number line. Oops. Try that again. -2, 2, and 3. Where is it positive? After -2, but before +2. And then after 3. What's its degree? Well, look at the number of factors and the kind that they are. There's 1, 2, 3 factors, all first degree. So the degree is 3. Let's count it. 1, 2, 3. Let's look at the turnaround points. 1, 2. Add 1 to that, your degree is 3. This time we went up, down, and up again. Same as last time. Let's try another one. This graph looks like the letter W, doesn't it? What are the roots? What do you see? About -4, -1, 0, and 3. -4, -1, 0, and 3. Have you noticed by now that we can only go from the negative region of the y to the positive region of the y if we go through one of the roots? That's the whole point of looking at the number line. So we start out positive above the x-axis, then we go negative, then we go below, then we go above again, and below, and then finally above. So these are the doorways. Each one of these roots is a potential doorway. Now, not every root allows the graph to go from negative to positive or positive to negative. Only the odd degreed roots. Now remember, degree is more than just the overall polynomial. It's also the factors. So each one of these factors, x plus 1, x minus 3, x plus 4, each of those is a first degree because the highest exponent on x is 1, and it allows the graph to pass through. The degree here, 4. We can count it 1, 2, 3, 4. The number of direction changes, down, down, and up. Now, most textbooks will say, look at the direction changes or the turnarounds. 1, 2, 3, and add 1 to that to come up with 4. However, some graphs not easy to do that way. The one after this one, you'll see. Alright, so what's going on here? -3, -1, and 5. There's only 3 roots, but what is the degree? Well, looking at the equation, you have a second degree, a first degree, and a first degree. So the degree is 4. And we can count it by going 1, 2, 3, 4. Fourth degree. However, not all the roots allow us to pass through to the other side. This root on -3 bounces it. That's right, just like a big burly bouncer standing at the door saying you can't come in. The graph bounces off of -3, so it's positive before and it has to return to positive. But then at -1 it finds a door to go to the other side of the x-axis because the degree is 1. So it goes through, and from 1 to 5 it's negative, and then finally after 5 we're positive again. Direction changes, down, up, down, up. Now, this graph, honestly don't know how you would come up with the degree if you just looked at turning points, because I only see this one. But the degree is not 2, the degree is 4. 1 here and 3 here, 4. Also notice how the leading coefficient, -0.1, is turning the graph upside down. This graph's end behavior is that it's coming from the bottom, leaving to the bottom. So what are the roots? Well, we see one here at -4, and then another one at 0. Notice that whenever 0 is a root, the factor associated with it is just x, right here. So, what happened at -4? Did the graph pass through? Yes, it did, but it passed through in a very special way. Went from negative to positive here and then back to negative. But this particular kind of root is called a point of inflection. An inflection point is a change in concavity. What's concavity? Concavity is basically a way to describe how the graph is changing. Think of it as being a cup, or part of a cup. If it dumps the water out, it's downward concavity. If it collects water or holds it, it's positive concavity. Somewhere in here, there's a change in concavity. To know where it would be exactly, you would have to use calculus. But you can see from up here that this is definitely dumping water out. This is a negative concavity all the way to the end of the graph. Well, when the point of inflection is on the x-axis, you have a point of inflection and you have to count the degree this way. 1, 2, 3, 4. This is a 4th degree. It goes up, point of inflection, then it goes up again, and finally down. That's how we can count 4. 1, 2, 3, 4. Finally, another W-looking graph. This graph's equation is not factored, but by looking at the intercepts, -1, +1, and the behavior at 0, where it's bouncing, we can factor it. The bouncing on 0 would be x squared. The -1 root would be an x plus 1 factor, and the +1 root would be a -1 factor. The roots -1, 0, and 1 show us that at 2 of the roots, we're able to pass through from negative to positive. But at 0, we get turned back. Oops, that wouldn't be positive, would it? It's positive here, goes into negative, tries to come back out to be positive, hits that root, and gets turned back down, negative. Finally, we find a root we can go through, and we're positive again. The degree, 2 ways to find it. Easy way to find it, look at the equation, highest power 4. Or counting, we have 1, 2, 3, 4 direction changes. Going down, and up again. Now I'm on Desmos. So here's the constant at A5. This is the number at the end. It's changing the y-intercept. Here's A1. A1 is the coefficient of the x to the 4th term. You notice how it looks a lot like a parabola, but it's not. It's more rounded on the bottom. When A1 is positive, it looks like a U. It comes from the top, leaves to the top. We flip it around to negative, comes from the bottom, leaves to the bottom. This A2 is controlling the cubic. So there's that classic cubic shape. Positive coefficient comes from the bottom, leaves to the top. Negative coefficient comes from the top, leaves to the bottom. That would be true of all odd degrees. Remember, degree is the highest power of x where the coefficient is not 0. So as I change these sliders, I'm able to change the degree. Now A3 is on x squared, so this is a quadratic. There's our parabola shape. Positive number, and you've got it coming from the top, leaving to the top. Negative coefficient coming from the bottom, leaving to the bottom. And a to the 4th is our linear component. These are positive slopes, these are negative slopes. Polynomials, especially this one will do 4th degree, are just combinations of these different powers and the interplay of their coefficients.